unnerving because I can't see any of you. All I can see are my own slides.
Boa noite a todos.
Boa noite.
Boa noite. Good morning, Paul. I think we are on air.
Good morning, Célio.
No, it's good evening.
Good evening.
I will first speak some words in Portuguese to the general audience, and then I'll come back to introduce you.
Okay.
Então, pessoal, nós estamos então iniciando esse webinar que no primeiro dia dos nossos encontros universitários da UFC de 2021, no qual nós temos agora a participação do professor Paul Webley da Monash University na Austrália, em Melbourne. E para o nosso grupo de pesquisa e para o nosso programa de pós-graduação em Engenharia Química, é uma grande honra ter este webinar com eu diria que um dos momentos de mais brilhantismo dentro dos nossos encontros, e especialmente tendo a participação de um colega pesquisador tão produtivo e reconhecido internacionalmente. Então, está comigo aqui o Paul e está também minha querida amiga e coordenadora do nosso grupo de pesquisa, a professora Diana, que vai me ajudar coletando perguntas do YouTube onde elas vierem. Porque pelo sistema que a gente está aqui, a gente não vê o YouTube. Então, vamos aproveitar e eu agradeço a presença de todos que estão aí, não sei quantas pessoas tem, que a gente não vê o YouTube, depois Diana vai me informar.
Temos 47 pessoas assistindo no momento, e vão chegar mais.
Já temos 47 pessoas assistindo. Bem-vindos todos e vamos começar.
Célio, se me permite...
Sim.
Se me permite, apenas antes do seu início, eu gostaria só de esclarecer e pontuar que esse webinar faz parte, o professor Paul Webley faz parte do projeto CapSprint. Nós temos 17 projetos CapSprint aprovados pela UFC, né, que tem por objetivo estreitar relações de colaboração científica internacional. E nesse sentido, durante os encontros universitários, alguns desses projetos terão esse momento, né? E o nosso projeto é especificamente sobre captura de CO2 e conversão de CO2, que é o tema, não por acaso, da fala do Paul Webley. Só esclarecer isso, Célio. The word is yours.
Okay. So now, Paul, in English now. So we are very honored to have you with us. As Diana was saying in Portuguese, you are an important collaborator in a project that's supported by the Brazilian government that involves collaboration with several foreign universities. And it's very, very honorable to have this opening webinar in this program for our university, especially in a topic that you are one of the top renowned specialists in the world. So before I open the floor for you, I will just give a brief introduction about your history and how you got here at this moment as one of these top researchers in the field of CO2 capture and conversion. Paul is, he had his bachelor's and master in the University of Natal, South Africa, followed by another master and a PhD at the MIT in Boston, or better, Cambridge, United States. He specializes in gas separation and processing technology, carbon capture and storage engineering, thermodynamic and techno-economic modeling of chemical processes, including hydrogen and future fuels production. He is a fellow of the Institute of Chemical Engineers at the United Kingdom. He is the vice president and future president of International Absorption Society and former director of the two centers for carbon capture in, I suppose, an Australian program. He has over 300 papers in refereed journals and books, 10 patents, and more than 100 contributions, plenary lectures, and keynote speaker in international and national conferences, with an H index of 61. Paul is now. He's been he entered the academic field as director of the MIT School of Chemical Engineering Practice, and later he had appeared as lecturer. He had appeared as engineer in products and chemicals, and then he joined the university, Monash University in Melbourne, since 2006, and now he's the director of the Woodside Monash Energy Partnership at that university, and he is also a full professor there. He's been head of department and all those typical academic positions. He's editor of a couple of international journals. He was the chairman of the last international absorption meeting on conference on fundamentals of absorption in 2019, very well organized in a nice location in northeast Australia. And well, there's plenty here. He's a guest editor of the journal Absorption. So Paul, enough of your CV. That's very long and full of nice things. And most of all, you are a very good friend and a very good collaborator. I must mention here your very generous help when we had a very severe COVID problem here in our region, and you offered your help, and you actually helped a lot in proposing, let's say, a short, small and economical way of purifying oxygen for emergency use in small units, in small hospitals or in small health locations. So we are very grateful to this collaboration, and also to the collaboration we have through the project, the international project that Gianna coordinates in our university. So his talk will be on advances and challenges in CO2 capture and conversion. So we are anxious to hear you. The floor is yours, Paul.
Well, thank you very much, Célio and Diana, and indeed for all the organizers to invite me. I'm very honored to be opening this webinar session. I think I always cringe a bit when people read all the things off a bio, because it's the most important thing is the friendship that we've struck up and the collaboration, and that probably means a lot more than all the other things do. And I'm just dying to get to Brazil, and I know one of these days we will be able to get back on the airplane and fly all over the place. And I do have a special time set aside where I do want to come and visit you, hopefully in good weather in Brazil. But it's definitely on my future travel plans. So and I would extend a very warm welcome to my collaborators in Brazil. I saw you all during the Cairns conference, and I'm sure I would love to see you all again now at Monash. And maybe just before I start to go through the presentation, you'll see on the first slide that Woodside is featured next to Monash University, and I'll just say a few words about that. Woodside is a very large LNG company in Australia. They operate in the Northwest Shelf in Western Australia, and they provide about 6% of the world's LNG, which doesn't sound like a lot, but it's an awful lot of LNG. And they extract it from under the seabed and liquefy it and then ship it to Japan and Korea and China and other countries. And they, like most oil and gas companies, have realized that they won't have a business model by 2050 unless they start to decarbonize. And companies all over the world, and I'm sure Brazil is no exception, have also realized that they need to decarbonize. And so Woodside has partnered with Monash University to say that it's not just a bits of research we're going to give you. We actually want to sign up a long-term, very close partnership, maybe 10, 20, 30 years, where we can work together and understand how we can decarbonize a company which relies on carbon for its major sales. It's very, very complex challenge, but a huge challenge and an exciting challenge. And I'm very honored to be the inaugural director of that program to help them decarbonize. So without any further ado, let me go to the first slide and just introduce a little bit about what I intend to talk about today. Firstly, I won't iterate too much about the need for carbon capture and utilization and storage, but I do want to say a few words about that because it underpins a lot of the research that we do, and it's also quite a controversial topic, and it's not widely accepted around the world that that is something that needs to be done. Then I'll move straight on to the subject that's near and dear to my heart, which is carbon capture using adsorbent systems, and just talk a little bit about some of the needs and challenges and show you some of the work that we've done in our lab and how that may help with some of those challenges. And then I want to turn to carbon utilization, because using carbon is an interesting thing to do from a thermodynamic standpoint. You know, as a thermodynamicist, you're crazy to use carbon for anything because it's the end result of a combustion process. But humans do crazy things, and so that's something we're looking at right now to try and understand what are the opportunities there. And so I'll talk a little bit about that, and then I'll make some concluding remarks about capture and utilization. So let's start off with the first one, and I apologize if the text in these figures is too small. I might just explain, just in case you can't read them. But the International Energy Agency, the IPCC, any of the major credible, authoritative think tanks and organizations that have studied how do we reduce our carbon emissions to net zero by 2050, they come up with various scenarios, and the scenarios involve reducing the amount of coal-fired power, reducing the amount of emissions from industry, substituting renewable energy for gas, and so on and so forth. But all of those models always have this little piece in there. It's not a lot, it's about 15% in the IEA models, which says we're going to capture carbon dioxide from these sources, these polluting sources, and we're going to sequester it underground. And that's going to constitute 15% of our flow of carbon. And it's sort of there, and it's always projected, you know, starting at about 0 now up to about 15% by 2050. But if you really go through the numbers of what that means, it's an enormous challenge for us. So if you think about how much we emit this year, and there's a lovely website you can go to, it almost looks like it has a doomsday clock on it, that tells you and counts how much CO2 we're emitting every second. And it's up to, I checked it this morning, it's up to about 39 gigatons. Now, what is a gigaton? A gigaton is billions of tons. And so we're almost at 40 this year. We're almost back to where we were pre-pandemic. So pre-pandemic, we were at 41, and we're now at 40. So the pandemic has really only represented a tiny little reduction for a couple of years, and we're back, and every projection is back to increase. How much have we captured at the moment? I've been working in carbon capture and storage for 20 years. There was a lot of hype about it, and we're now in 2021. And this bar chart shows you, and I don't know if you can see the laser pointer, I'm hoping you can, but the light blue shows you how much CO2 we're currently capturing and storing underground from natural gas processing. That means that CO2 that comes out the ground with natural gas, and we take that natural gas, we separate it out from the CO2, and we re-inject the CO2 either for enhanced oil recovery or for other purposes. But that large section is currently what we're doing. And a lot of that is the big LNG projects around the world. And Gorgon, which is a big project near Australia, will have quite a bit of that. The dark blue is fertilizer. So when we make fertilizers from ammonia, we produce CO2, and that CO2 can be captured and transported and sold either for use or for enhanced oil recovery. And then the other little sectors that you can see are tiny amounts: chemicals, synthetic fuels, power generation, bioethanol, steel, hydrogen. So by 2021, we have captured a total at the moment every year of about 41 million tons, and we emit 40 billion tons. So we capture at the moment 0.1% of the world's CO2 emissions, which is so tiny. It's almost negligible. And so if you think, well, by 2050, we have to capture 15% of that 40 billion tons, we really have to get cracking and start building capture plants like crazy. So to that point, if you look at the next slide, this shows you the world-class carbon capture and utilization facilities operating and in development between 2010 and 2020. You can see there's three colors here. The light blue are ones that are operating. The darker blue is ones that are currently under construction. And the light green are CCUS projects that are sort of at an advanced stage of development. And then the light green, or the top green ones, the darker green, is in early development. And you can see that we had quite a lot of projects on the table in the mid-2000s, 2010, 2015. And then we went through a period, and I remember this very well, 2015, 2016, 2017, where you could not get funding for carbon capture work at all. People had lost interest, a lot of fatigue had set in. And I think what's changed in the last 2 or 3 years is the urgency of climate change has changed, and the willingness of people to pay large amounts of money for carbon offsets. We've seen recently companies in the carbon business sell carbon offsets for $1,000 a ton. And that starts to look really, really interesting, especially when you're in countries like the USA, where you can get $45 a ton revenue for sequestering CO2. So at the moment, where I think we're on the uprise again, whether we're going to make 15% in the time available is a guess. I think we're going to have to be very, very aggressive and very ambitious. I also think carbon capture in the early days was very much focused on coal-fired power plants and capturing CO2 from coal-fired power plants. While I still think that will happen, I think it's become more and more difficult politically to sell that concept, certainly in Australia. I think we are much more likely to replace our coal-fired power plants with solar and wind plants before we would ever get the funding to build a capture plant and capture the CO2. And I don't think it's about technology. We know the technology works. We can capture CO2. We know how to store it. It's about the optics and the politics around why are you doing something to perpetuate the coal industry. We saw at the last COP26 that there was a call to phase out coal completely. So you would be a very brave investor to invest in a capture plant that's attached to a coal-fired power plant where the lifetime of both of those entities are 20, 30, 40 years in terms of their economic payback time, but it's very unlikely that your coal-fired plant will be able to run in 40 years' time. So I think our early deployment of carbon capture and storage has to be outside of the power sector. And so what does that mean for us as researchers? Capturing CO2 from flue gas, while it's interesting, is probably not where the early gains are going to be. And so personally, I've put that aside as something that's something to be picked up a bit later maybe, but at the moment I'm focusing on other things. And I think there's a more urgent need for carbon capture in some of these areas that I've indicated on this slide. Hard to abate sectors. So there are some sectors of our economy. The cement industry is a classic example. Iron and steel. The chemical manufacturing industry releases a lot of CO2. It's part of their process. They can't help release it. It comes through when they're manufacturing a chemical. One of the byproducts might be CO2. Those are sectors that we are actively working with at the moment to understand what does it look like, what does capture look like in those sectors. The second one that I think there is going to be a great need for CCUS is in hydrogen production. And hydrogen, of course, has been the buzz for the last 5 years, 5 or 10 years, and it's increasing every day. There's new projects announced around the world. Many of them are driven from renewable energy, but that has got its own set of problems in terms of cost and scale. And in the short term, producing hydrogen from natural gas and then sequestering the CO2 will allow us to produce gigatons a year of hydrogen at low cost, and will jumpstart the hydrogen economy. So that's going to be a really important area for us to look at. How do we efficiently strip out the CO2 from hydrogen production? And then the last thing I think that there's really going to be a lot of need for is on the negative emissions side. And increasingly, it was certainly true in COP26 in Paris, but increasingly there is a requirement in a lot of these scenarios and projections and plans and roadmaps for how do we decarbonize. There's a requirement that by 2050, there's a good 5% of our emissions have to be negative emissions. So we have to be capturing from the air in some way, biologically or through a direct air capture system, and we have to be sequestering that CO2. And in that way, we can try and mitigate the overshoot, because we're going to overshoot our aspirations for 1.5 degrees. That's almost certain. And we'll probably overshoot the 2 degrees. How do we claw back some of that carbon budget? And one way to do that is negative emissions. And so these are the areas that I would encourage people to focus in on carbon capture. They're going to be the areas that are going to be the early deployments, and are going to be the areas that I think will help jumpstart the options. I should also mention, it's not on the slide here, but generating very high purity CO2 using the Allen cycle with natural gas is increasingly something of great interest. It's a very efficient cycle. It uses oxygen instead of air for burning. It produces a stream of 100% CO2 at high pressure, ready for sequestration, and generates electricity at about a 60% thermal efficiency, which is fantastic. It's almost unheard of, and rivals renewable energy generation. So those are areas that all are going to require carbon capture, utilization, and storage. So I'm going to turn now, in the interest of time,
can you hear me,
on my clock here. Absorbent systems is something we've been working on for 20 years to try and do capture. There's still a lot of work going on. There are no commercial, large-scale post-combustion systems that use adsorbents. They all use absorbents. And I show here just a diagram of one that's probably the closest to commercial reality. And this is a company called Inventus. They're now called Svante, and they are in Canada, and they have a adsorbent placed on laminate sheets, rotating around a sort of a merry-go-round, where you have in stream 1, flue gas flows in, you capture the CO2, and you vent this CO2 lean gas. Then this adsorption section moves to another section where steam strips off the CO2, collects the product, and then we have to condition the material so that it's ready for reabsorbing. We do that with flue gas, and then the adsorbent moves to the final section where it has to be cooled down because it was heated up, and then it's now ready in the cool stage to go back into the vent. So you can see there's a little diagram, a little photograph here of the system. It's quite a small system, a few tons a day, but this uses an adsorbent to do capture, and a very, very specialized adsorbent that has to be coated onto laminate sheets, and to make sure that we don't put a lot of pressure drop on the system. So you can see that we're sort of at the technology readiness level 5, 6 with adsorbent systems in comparison to absorption systems, which are, of course, operating already and have been for many years. So in terms of the applications, we've been looking at CO2 removal from the tail gas of hydrogen PSAs. Hydrogen PSA separates CO2 from hydrogen to produce very pure hydrogen. And its waste gas contains still a lot of hydrogen, maybe 10 or 15%, but has a lot of CO2 in it. And that's very, very useful. Instead of taking that gas and venting it or burning it, we can recover the CO2 from that gas. I mentioned earlier, cement, iron, and steel are systems that we're looking at. And increasingly, I don't think there's an academic lab in the world that isn't looking at direct air capture. It's certainly got the attention of investors and banks and engineers, and in fact, Woodside is very interested in direct air capture. The reality, I think, is always a lot more sober than the excitement around it. Landfill gas and biofermentation is an area that hasn't got a lot of attention, and I think it should, because we potentially there have a opportunity for negative emissions. And I think there's a lot of landfills out there that are not being, the gases are not being treated because it's too expensive to treat the gases, and they're being emitted or they're being burnt. If there is an opportunity to capture that CO2 and store it, you actually have a negative carbon flow, and potentially you could earn carbon credits if you did that. And so all of these applications have in common rather good things for absorption. The CO2 concentration is often quite high, 30 to 50%. That's certainly more than flue gas. The challenge for us as absorption engineers is they're multi-component systems. We have difficulty, and all of us who study absorption know about multi-component systems. We have difficulty measuring multi-component isotherms. We have difficulty modeling them, especially if there are 5, 10, or 15 components. Our simulators take a very long time to simulate a 20-component system. We've got this thing called moisture, which is very, very irritating, but unfortunately, Mother Nature has put it into everything that we do. And so any system that we look at, we have to think about the fact that it's going to be wet, and how are we going to handle that with our absorption system. We have to make very high purity CO2 for many applications, although later on I'll talk about the fact that we could potentially make much lower purity if we integrate it with capture. But making high purity with absorption is quite difficult when the molecule you're trying to purify is strongly absorbed. And in this case, CO2 is strongly absorbed. The other gases, like nitrogen or oxygen, are not strongly absorbed. They're weakly absorbed. And so they are eluted from the top of the bed in high purity. It's very easy to make them at high purity. It's very challenging to make the CO2 at high purity. And so that's a challenge that we face with an absorbent system, which they don't face with absorption. In absorption, high purity is made almost automatically. And the final challenge I think we face in absorption systems is the flow rates are very, very large. And that means typically with any solid system, the equipment is very large, because we don't get a lot of absorbent in a net volume. And to that point, on the next slide, these are just some photographs I stole from reports on direct air capture plants from 3 different companies. On the left, Climeworks, in the middle, Carbon Engineering, and on the right, Global Thermostat Facilities. And these sort of indicative photographs show you the sort of footprint for very small plants, by the way. These are probably 1 to 2 ton a day plants. And if we need to sequester 1 million tons per day at a plant, can you imagine something 1 million times this size? So it's been calculated that a direct air capture plant, to capture the CO2 from a 500 megawatt power plant, would be about 30 kilometers squared in terms of its footprint. So direct air capture as a solution to all of our problems is definitely not going to be the solution. They are very, very large. Many of them, the ones on the left and right, rely on solid absorbents. The one in the middle relies on a liquid system. And so potentially, I think if we're going to go down the route of adsorption for carbon capture, it has to be very much focusing on our strengths. So smaller scale, higher pressure, higher CO2 levels, where we can have an impact. So what are some of the challenges? I'm going to talk a little bit about some of the challenges, and then show you quickly some of the work that we've been doing. We need a high working capacity for CO2 because we have such high flow rates. So we tend to favor chemisorbents rather than physisorbents, because chemisorbents have a strong chemical bond to the CO2. We have to produce high selectivity materials. If we don't have a very high selectivity, that means that we obtain a lot of the other molecules that are in the gas stream: nitrogen, methane, oxygen. They're very similar in size to CO2. So trying to separate them purely on the basis of size is very difficult. If we separate them purely on the basis of how strongly they attach to the surface, then all of those molecules attach to various extents. CO2 the strongest, but nitrogen, methane, and oxygen will also absorb. So when you go to recover that CO2, you will also recover those other molecules. We'd rather not absorb the water if we can help that. That's very, very difficult to do that on an adsorbent. And the last thing I'll talk about in a few minutes is about the physical structure of what the adsorbents look like. But let me turn first to processes. CapEx and plot space are going to be very large. And that's something that we have to think about when we have an adsorbent, is how do we design that plant? I've highlighted in yellow probably the most challenging and difficult aspect of using an adsorbent to capture CO2, and that's the heat transport aspect. We are going to need, if we have a chemisorbent, we have to heat the adsorbent to release the CO2. And you know as well as anyone does that heating a solid is very much harder to do than heating a liquid. And that's what we're trying to do. An adsorbent is a solid material. And if we have to heat it, and then even better, if we have to recover that heat, because we don't want to lose that heat, we would like to try and recover it and use it for the next cycle. That's very, very difficult to do in a solid. And in my opinion, it's probably the major reason why a temperature swing adsorption system for solid adsorbents is going to have difficulty competing with a liquid system. Is because of recovering that heat and reusing that heat. It's exceptionally difficult. It doesn't mean we can't try, and there are some very novel ways about doing that, but it's something we really have to focus on. And that's not an adsorption chemistry challenge, it's an engineering challenge, it's a heat transport challenge. I talked about pre-drying. I don't think it's legitimate to pre-dry when you're going to use 1 to 2 gigajoules per ton of CO2 just to dry the stream. I think we have to be able to accommodate the CO2 as is. Temperature swing processes tend to be favored because of the chemisorption angle, but as we all know, heating and cooling solids takes time. How do we do that really fast? We could use fluidized beds, we could use moving beds. Those are options. So engineering the system, I think, is very, very difficult. And then I think the other thing that we still need to work on is better PVSA cycles. For smaller scale applications, we can switch to pressure swing adsorption because the throughputs are smaller and you have smaller working capacities in pressure swing cycles. So I'd like to just show you an example, a couple of examples, or just one in this case, of some adsorbents we've been working on that have very high selectivity. This was published in the International Industrial and Engineering Chemistry Research Journal. You can see the title at the top here in our group. And this was a collaboration with some of those people are some of my ex-students, some of them are postdocs, and some of them were at the University of Melbourne, some are in Hong Kong. But it was a collaboration to try and understand, can we use these new zeolites that well, new zeolites that are actually very old, but zeolites that what we call trapdoor zeolites, to separate carbon dioxide and methane. And trapdoor zeolites are zeolites that have the ability to change the position of their cations to uniquely allow admission of CO2 and prevent the admission of methane. And you can see probably the better diagram to look at is on the right-hand side here. This is the amount adsorbed in moles per kilogram. And these lines up here is the amount of carbon dioxide. And these are, to those of you familiar with adsorption, this will be a strange plot for you. It's not an isotherm plot, it's an isobar plot. It's a profile of isobar. So we're keeping the pressure constant on these lines, and we're changing the temperature. And you can see, let's follow the green line, for example. This is CO2 absorbing. As I start at 1 bar, as I start decreasing the temperature, I get more and more adsorption. As you all know, adsorption is exothermic, so you get more adsorption as you drop the temperature. And eventually, it just keeps going up, and it will keep going up, and I'm getting a nice lot of adsorption, about 1.5 moles per kilogram. If I look at the same thing down here for methane, and I follow, let's say, the pink line, I start getting more and more adsorption, which is what you'd expect. But at some point, the adsorption plummets down to 0, and I get no adsorption at all. And this is what we call this molecular trapdoor effect. We're finding that at some point, the cations and the methane interaction is such that it can no longer, the methane can no longer squeeze its way through past these cations and into the structure, and its absorption goes to 0. So if we operated a pressure swing adsorption process below 275 down here, we should theoretically get a very, very good separation, essentially no methane separation and a lot of CO2 adsorption. Now, of course, 275 or 273 is 0 degrees Celsius, and it's difficult operating a PSA at 0 unless you're up at the North Pole, at the South Pole. And so typically we tend to operate them a bit warmer. So what we've done is we've looked at some studies up around between the 290 to 300 region, where it's still less methane absorption, but still a little bit, and to see what performance we can get. And at least for the mathematically inclined of you, we can model these interesting isotherms quite well using a simple isotherm model, and then a factor which accounts for what probability and what is the probability of these trapdoors being open for methane as a function of temperature. And we've published a paper in Nature Communications on that, if you're interested in that. And then we came up with a simulation system that allow us to actually see what we get. And so we have a single bed that represents 5 beds. We feed and absorb and remove the methane, absorb the CO2. We depressurize to blow down, because we're feeding at 20 bar, blow down to 1 bar to get rid of a lot of the methane. And then we desorb under vacuum, and that removes a lot of the CO2. You'll see we'll still have a lot of methane in the void space, so we are going to get contamination of that product and then repressurize. But we were very successful in obtaining very, very high purity methane. You can see the CO2 purity is not too bad. It's around 65%. Going up from 15 to 65 is pretty impressive. And it would require us to do 2 things. One, to drop the temperature of this bed down to 0, and that will give us 0 co-absorption of methane. And the second thing is perhaps to change the cycle, introduce more sophistication. But it's a very promising result and shows you that there are adsorbents out there that can be uniquely tuned to this application. So on that note, I'll just take a step back and just talk generally about adsorbents. And I think I sort of classify them as 3 generations. The first generation of adsorbents were ones that have been used since antiquity, since the 1800s, or if not before, are naturally occurring things. They are things that our ancestors found in nature, and they took them and they used them as is, and found that they helped with, removing odors from a region or something, or removing toxic chemicals from wastewater. And it was trial and error. And that was our first generation of adsorbents. And then I think we started learning between the 1940s to the 1990s, learning how to make those naturally occurring materials synthetically. For example, making our own activated carbon adsorbents from polymers, or making our own zeolites, and synthesizing our own structures, learning from nature, and then modifying them, either post-modification or pre-modification, and then using those in an adsorption process. And so that was all the fields of new zeolites and new crystalline and carbon and silica materials that have been developed, and that by and large we still use today. And then I'd like to think that we've now sort of entered the era of the 3rd generation of adsorbents, which are really in its infancy now, where the adsorbent material in the past was always inert. You made it and you put it into place and it worked. We're now starting to see adsorbents which are active. They actually involve themselves in the adsorption process, and they can flex and they can change, and they are much more dynamically involved in the separation process than the 2nd generation ones were. And I'd like to give 2 examples of those. And we have a paper coming out in Chemical Society Reviews very soon, summarizing all of these very interesting effects. And you'll see on the top, there's 3 sort of mechanisms. One is what we call framework deformation of the adsorbent structure. One is vibration of pore keeping groups, and the other one is oscillation of extra framework ions. And those are sort of 3 mechanisms that you can get. And within each of those mechanisms, the system can change, either because it's interacting with the molecule that you've put in there, or you can apply some external stimulus. So for example, framework deformation, we've all seen this if you've worked in metal organic frameworks. There are some molecules you can put into a metal organic framework, and right away it changes the framework flexibility, almost like an egg crate that gets crushed. As soon as you put the molecule in, it distorts the framework. You can apply an electric field or a electromagnetic field, and you can change the shape of that framework, and in doing so you can change its adsorption properties. The pore keeping group are really interesting. They are atomic molecular groups within the pore spaces, like benzene rings or other structures that are flexible, that can move. And so if you externally stimulate them or you interact with a guest, they shift, and in their shifting, physical shifting, they open up more space and they allow access to the internal space. And the one that's our favorite, which we've worked on a lot, are in zeolites, are cations in the zeolite that can move, and we can move them with other molecules, or we can even move them. We've been trying reasonably successfully in the last 6 months to try and move them electrically, and that allows us to open and close the adsorbent and come up with a true electrical swing adsorption that's not just heating, but is actually shifting the structure. Let me turn to the next one. That just shows you again an example at the bottom of, in this case, I've got an adsorbent. I'm shining light onto it, and when I shine light onto it, it changes its structure. It actually gets smaller. The framework contracts. And it's because the linkages in the framework are made with molecules which undergo a cis-trans conformation when you shine light on them. And so they become smaller and they exclude molecules. And you can see this wonderful isotherm. This is not our work, where you can almost see the two isotherms here. And we can switch between the two by shining light onto the material and then removing the light. And you can see how the CO2 isotherm steps up and down. So a wonderful example of a material where you could potentially have light stimulated adsorption. And then before I move into utilization discussion, structured adsorbents are materials that are basically the same adsorbent, but we no longer have them in beads. And we've become accustomed to beads and granules and pellets because that's all we had for the last 100 years. But increasingly, I'm seeing the need that the adsorbent is actually not the major part of the process. The process itself dictates and informs what the adsorbent should look like. So we may have to start looking at doing much more research. Our adsorption community needs to do much more research on forming the adsorbent into a form that's more appropriate to the process, other than just saying, we've made crystals, we've made them in lab, we've made pellets, here you go, engineer, go and deal with them. That's no longer going to be enough. We really have to be much smarter about how we make the adsorbents. So let me just turn my attention. We've got about 5 minutes. I won't go through a lot. Carbon utilization is something that we increasingly are getting into. And it's really a process of capturing the CO2 and then doing something with it. You can either make chemicals and fuels and building materials with it, or you can actually use it as is for a lot of applications. And I think in both instances, you're going to need the CO2 either high purity, or you're going to need it at high pressure. And the CO2 can come from a range of different sources here. So we've been very interested in combining our adsorption knowledge with reaction to try and improve the CO2 utilization. And the reaction we're looking at is making methanol from CO2. And a lot of people are doing this, reacting carbon dioxide with hydrogen to make methanol, and we also make water. That's a reaction limited by equilibrium considerations. And so you can imagine that anything you can do to change the local concentrations of these species wherever the reaction system is occurring will have an effect on the process. And this table just shows you a typical list of all kinds of catalysts. They're typically copper, zinc, alumina, and operating at 30 bar. You can see the conversions are very low. Those are unfortunately is a compromise between kinetics and temperature. It's an exothermic reaction, so we'd like to run it as low a temperature as we can in order to get the equilibrium to shift to the right. But by doing that, the temperature is so low that there's no kinetic ability, because we can't get over that activation barrier. And so we're trying to retain the temperature and add some adsorbent to boost the CO2 concentration. And I won't go through all of this text here, but really it's the motivation behind what our work is. We took a commercial adsorbent, we ground it up into a powder, we took a hydrotelsite adsorbent, and we mixed it with that catalyst to see, does the presence of an adsorbent right next to the catalyst help this process? And just to show you this nice little reactor that we have, most groups have got that. You probably have them at your university. And this on the graph just highlights the fact that the conversion and yield that we get commercially with a commercial catalyst are so far away from equilibrium. You can see how heavily off we are from equilibrium. And therefore it gives us some motivation that we have still quite a long way to go. So what we've done now is we've mixed our catalyst and our adsorbent, and we call them CH0 means it's a copper catalyst, a hydrotalcite. It's got 0 amount of hydrotalcite. So that one there is all catalyst, and then CH100 is all hydrotalcite. We had to make sure that the hydrotalcite wasn't catalytic. And you can see between it's, we would have expected if the hydrotalcite had no role at all, we would just linearly decrease as you decrease the amount of catalyst in the bed. And that's not what we saw. We saw quite a lot of retention of the conversion, even up to 40% hydrotalcite. So we can see that there is a positive effect here. It doesn't help us with the conversion because we're still stuck with the copper catalyst, but it does help us to retain that and reduce the amount of copper. And interestingly, increases the selectivity quite remarkably. So going from about 68% up to 74%, and increasing the methanol yield. So very interesting results. And obviously we have a long way to go to explore a lot more of these. We did some great control experiments where we mixed the hydrotalcite in a pellet form with the catalyst, just pellets next to each other. And you can see we don't get the blue bar in the middle is the hydrotalcites with pellets. The right-hand one is the intimate mixing of the powders. We get nowhere close to the same type of conversions. And so it seems like we need to have that adsorbent right next to the catalyst. And our next stage, and I won't have time to talk about this because I'd like to close off, but the last stage is to actually to precipitate and form the copper catalyst on top of the hydrotalcite. And that has its own set of challenges, and I'm not going to go through that in the interests of time because I want to just close off with some general comments. So the challenges of integrating capture with utilization, I think, are going to be first and foremost, if you look at a conventional capture process like this is a liquid phase one. We absorb the CO2, we have to strip it out, we have to compress it. This is where all the energy is taken up, the reboiler and the compression. And that's where the 2 to 3 gigajoules per ton comes in. How do we lower that? How do we actually get rid of that? And there's a lot of interest to say, why don't we just get rid of this part of the flow sheet? We capture the CO2, and then we use that amine captured CO2 structure to do something with. Or we capture the CO2, but we don't capture it at high purity. And so I think some of the challenges that we hopefully can overcome in the years to come is that there is a very high capture cost burden for the subsequent the U part of the CCUS. We're all interested in using CO2, but we have to capture it first. And there are niche applications that rely on high purity CO2, but they're very, very few. Many of the applications for CO2 utilization, like the one I've just showed you to make methanol, if there's oxygen there, you're going to oxidize the CO2 right back to the products that you make, the methanol, is going to be oxidized right back to CO2 again. And of course, unfortunately, we are capturing CO2 from air streams that contain oxygen. So that means if we want to do a capture and a methanol process, we have to have very, very high purity, which is very difficult to do in a capture process. And so we have to think about how do we integrate capture and utilization in a much, much cleverer way. So one of the things that we're doing at Monash University, and this is still a work in progress, is we're setting up a research hub in carbon utilization and recycling. And it's got both the capture component and the biological conversion component in it, and as well as some other components in it. I'll just show you, and this is my last slide, is just to show you an overall. As a chemical engineer, I couldn't resist having the last slide as a process flow diagram. Our research hub that we're looking at, we've got, you can see 5 universities involved: Queensland, University of Queensland, Curtin, ANU, and ourselves. We'd love to have your university involved. Where we're looking at all aspects. We have electrochemical engineers looking at electrolysis. We've got people working on DAC. We've got a lot of expertise in these universities in the biochemical area. I'm very fond of the biochemical area, and the reason is that it can tolerate air. Nature has evolved in a way that can tolerate air, and the plants can use carbon dioxide and create plants. So they're going through a reduction process in the presence of oxygen. And so let's try and use that knowledge from plants and do something with it. The problem with biochemical processes is they are very slow to use CO2. They use CO very well. And so carbon monoxide can be used very easily from an electrolysis cell to make carbon monoxide and hydrogen and feed that into a biochemical process. So we do the CO2 to C1 chemistry thermochemically, and then we do the higher value chemicals biochemically, and then we come back in again with a thermochemical route to do the final post-processing of these biochemicals to these products here. And so I think this overall system is our approach as society and as a civilization to a circular economy, where we are extracting and using CO2 from various sources and ultimately bringing them back into the chemicals that we're consuming. So on that note, I'd like to conclude, and I really thank the conference organizers for the opportunity. I apologize for running long. We only have 5 minutes left, but I'd be happy at this point to take any questions.
Thank you, Paul. It's this moment that I miss the big audience, the clapping. Thank you for, very, very interesting talk and very full of things.
And maybe I'll stop sharing now.
To think about. We have some questions from the audience that I will try to read here. From
Paul, can you hear us?
Can you hear us, Paul?
I can't hear anything, so I'm not sure if this question is being asked.
Okay.
We knew, a gente sabia que ele não estava ouvindo ninguém.
Can you open maybe the sound? There's a chat on the right hand side that maybe.
Okay, I'm going to, I can't hear anyone, but I am going to read the chat. And so I'm happy to answer some of the questions on the chat.
Okay.
William had a question: how does the new technologies in vehicles and transportation significantly reduce the impact of emissions? I absolutely. I think it's been really interesting in my work, because I'm also doing a lot of work in hydrogen now, and there's a lot of interest in hydrogen and CO2. But I think first and foremost, electrification where we can is going to be the most important thing we can do. It's going to be difficult to provide enough energy for electro reduction of CO2, electrical production of hydrogen through electrolysis. That is going to take away renewable energy from all the renewable energy we need to replace fossil fuel. So in terms of priority, first priority is replace fossil fuel electrical generation with renewable electrical generation. To do that, we are going to have to build terawatt hours of solar PV and wind over the coming years, and we won't have a lot to spare for hydrogen. And so I think that's going to be really important to on the electrical front. My volume button is definitely enabled, and I can hear my speaker. I can change speakers, and I can.
Hello.
I can hear the volume of my speaker, so I don't think it's. Mute and unmute.
We're speaking here. But you
try
can't
another
hear.
set.
Hello. No,
Hello, are you there?
Can you hear us now?
Now I can hear you.
Okay, great. Finally.
Wonderful. Okay.
In the beginning of your presentation, I almost yelled to see if you could hear me.
Could you hear my presentation?
We could hear your presentation, but you couldn't hear us, and I wanted to.
No, I couldn't. All right, now I can hear you loud and clear.
Okay, yeah,
Good.
that's fine. So when you see this later, if you see this on YouTube, there will be a point of time that I was going, Paul. I wanted to alert you that there was a pop-up covering part of your slides, but it didn't. It wasn't too much trouble. But anyway, okay. Thank you very much, and for bringing us this very thoughtful presentation. Lots of things to think about. You already answered one question that came, and there is another one that is
the simultaneous capture of CO2, electrochemical reduction that also uses. Absolutely. So, I can tell you that the industries that we're working with and our new hub that we're setting up, we've got 15 companies involved, and electrochemical conversion has become very, very important. And it's a hot topic. You just have to Google that and you'll see everyone is working on electrochemical conversion. It has to use renewable energy, otherwise there's no point in doing it.
May I ask a question?
Go ahead, Jana. You're the boss.
Paul, maybe you're not aware of, but here in the northeast part of the country, there is the green hydrogen fever, which I think is also affecting Australia some way and Morocco and anyway. So the model that was chosen here was to use electrons powered by renewable energies to make sure it's really green. And my question, you addressed this issue a bit, is in your view, how do you think this competes with extracting carbon from biomass, from wastes, from other sources that are also renewable, but would require CO2 capture facilities to they call it blue, not green, actually.
Yeah,
so I know
that's
there's
right.
a regulation, but I wonder if you have a comment regarding where are we going to take hydrogen from in the future?
That's a very good question, Diana. I've just written an opinion piece for the Monash lens, which is our sort of general communications on blue hydrogen versus green hydrogen, because it's become very controversial in Australia. And the reality, in my opinion, is that we are going to need as much renewable energy as we can possibly get in the next over the next 20 years. And if we can just use that to transform our cars from petrol-fired to electrical vehicles, that's already going to eat up most of that renewable energy. We're not going to have enough to run hydrogen, but we are going to need hydrogen. And we are going to need fuels. I think some of the things like airplanes, ships are too hard to run with electricity. We're going to need fuels for them, and we have to get the fuels from somewhere. If we get it from hydrogen, I think the logical place to start is to take hydrogen from fossil fuels, do CCS, do it well. I think people also confuse, there's been a lot of publications on blue hydrogen being worse than gray hydrogen, which is just crazy if you think about it. But people saying, well, you've got all these other emissions, but we haven't in the past, our SMRs, our steam methane reformers, have not been built with a view to low emissions. They've been built to make hydrogen. If we put that flow sheet aside and redesign a flow sheet, that's job is to make hydrogen and to make a pure stream of CO2 ready for capture, that's a different process and a different plant. And I think that is the key for us in the future for the next 10 or 20 years is let's do really smart new hydrogen plants that are built to make hydrogen, but are also built as zero emission plants. So maybe they have to have electrical reformers. Maybe they have to have other sorts of opportunities in them. Biofuels, obviously Brazil is leading the world in biofuels. It's got a huge potential. And I think, so I think there's the hydrogen story, there's a lot of hype around green hydrogen, and it's fantastic that there's hype, but the reality is at the moment, if I talk to companies, they'll tell me, Paul, hydrogen is 10 times, green hydrogen is 10 times the cost of blue hydrogen. Yeah. So give us a commercial reason for using green hydrogen. No one is going to do a reason for charity at the moment.
Yeah.
Thank you, Paul.
Paul, there are some comments on the YouTube that are being brought to the main screen. I want to highlight a comment from our research director at the School of Graduate Studies and Research, Professor Gianni Andrade, congratulating and being grateful for your excellent presentation. It's being shown.
Thank you very much. Thank you for that.
So we are very honored to have you here, Gianni. Thank you for joining us.
Thank you, Célio. I would love to have been there in person.
You will. You will, hopefully. And I have a comment, fundamentals and the study of the materials, and then try to proceed to have a proper process and economic and feasible. So I want to make this comment about your talk. So there are many students listening to us, and chemical engineering has all to do with that. We have to know the basics, the materials, the isotherms, the kinetics, and to learn the processes to use them properly. So I was very impressed with this material, with the trapdoor characteristics. I wasn't aware of that. I have to look at that paper. So this is just a comment. If you want to entertain it in any way, but it's not a question.
Look, I would 100% amplify that comment to say that we're working on direct air capture here as well, and the people working with me are electrical engineers, mechanical engineers, and civil engineers. No chemical engineers, because it's all about what is it we want to do. The absorbent is just one little piece. Engineering the system is so important, and it almost comes up with the criteria for the absorbent later on. You almost say, I need a system that handles air like this, I need to flow it like this, I need to expose it like this, I need to have this pressure drop. You come up with a whole design of the system, and then at the end you go, and by the way, can you give me an absorbent that can separate this and this? So it's a different way of looking at the process, but it's definitely both have to work hand in hand.
Okay, thank you. And there was a question if the presentation will be available. And the answer is we had talked about it before, and Paul is allowing us to share the presentation on the UFC, the university website, and I think later the organizers of the meeting will provide details about how to watch it. So I think we are a little bit past our time. Thanks for keeping the time. We did delay a little bit in the beginning. I talked too much. I recognize that. But again, thank you very much, Paul. And I hope we'll meet you soon, probably in Colorado, I hope, in 6 months for the International Conference on Absorption, but also sometime soon here in Brazil and or in Australia. So
fantastic.
So with this, I want to. I don't think you heard my clap before because you were not.
Now I have. Now I hear it.
I said this is the one thing that I missed from the public presential presentation. There's the clapping sound. So I'm trying to emulate here because we had over 100, sometimes about 150 people watching. In average, about 120 people. So I'm sure everyone is clapping with me. So thank you very much.
Thank you very much.
And it was very honorable to have you here with us. So
All
I
right,
think now we'll close this. And I hope you have a nice day there. And on our side, we'll go to the beer.
All right. Thank you, Célio. Thanks all. Thanks, Diana.
Okay. Bye-bye.
Olá, meu nome é Vitória, sou aluna do curso de Medicina e estou aqui hoje para conversar um pouquinho com vocês sobre a UFC, a Universidade Federal do Ceará, a minha faculdade. Mas para começo de conversa, vocês conhecem o nosso Ceará? Nosso estado fica localizado aqui no Nordeste brasileiro.
E tem praias lindíssimas. Mais de